Have you ever wondered why, when walking into your home, you can tell when someone has been cooking? And not only can you tell when someone has been cooking, you can tell pretty much what they've been cooking. Now, the reason is that your nose contains receptors, and those receptors are made to a specific shape to fit the shape of different volatile molecules. So it is the shape of these molecules that allows your receptors to bind with them and to send a message to the brain to tell you what has been cooked. In this video, we're going to actually look at how to predict the shape of some simple molecules. The overall shape of a molecule is determined by the bond angles. This is the angle made by joining the nuclei together. So if you look at this one, you can see the bond angles are 180. Whereas if you look at this one, the bond angles created will be through here, which is 120. Now the bond angles of a molecule, together with the bond length, will precisely define the size and the shape of the molecule. So in this video, we're going to go through how to predict the shape of some simple molecules. To predict the shape of molecules, we're going to be using what's called the valence shell electron pair repulsion theory. The idea behind this theory is that the electron pairs in the valence energy level of an atom repel each other. Now this happens because they're both negatively charged. Therefore, what we need to do is we need to arrange those electron pairs as far apart as possible to minimize repulsion. Now there are different types of electron pairs. They're either bonding pairs or non-bonding pairs. Non-bonding pairs are often called lone pairs. And this theory allows us to predict the molecular geometry of a molecule. So the steps for predicting a shape. The first thing you're always going to have to do is draw an electron dot diagram. Then you're going to look at the number of electron pairs around the central atom. So it's always very important that we're looking at the central atom and the number of electron pairs around it. We need to arrange those electron pairs to minimize repulsion. You describe the molecular geometry in terms of the angular arrangement of the bonding pairs. So we look at the geometry in terms of the atoms, not how many electron pairs there are. And the molecules containing double or triple bonds, for the purposes of predicting a shape, are counted as one bonding pair. So we're going to look at some examples for some simple shapes. The first step is to draw an electron dot diagram. So we're going to do the example of hydrogen. So we know that each hydrogen atom has got one valence electron, so we have a total of 1 plus 1 is 2 electrons. Now there is no central atom because there's only 2 atoms, so you put down the hydrogens, and you start with a single bond between them. And now, because hydrogen is special, it only has 2 electrons around it, you can see that it only has one single bond. This means to arrange this as far apart as possible, you will get a linear shape. Now let's look at a second example, HCl. Now in this case, start with the electron dot diagrams. The hydrogen has got 1, the chlorine has got 7 valence electrons, so we're playing with a total of 8 electrons. Put down the atoms. Start by a single bond. complete the octets. Well, hydrogen doesn't have an octet, it only has 2 electrons, but chlorine does. Now there is no central atom here. To spread these as far apart as possible, you will get a bond angle of 180 degrees, which makes it once again a linear molecule. So here are some shapes that I've made up. This one here being hydrogen, you can see if we join the 2 nuclei together, its bond angle once again is 180 degrees. This one here is HCl, hydrogen chloride. Join the 2 nuclei together, you can see that the bond angle is 180 degrees. This time we're going to play with 3 atoms. We're going to look at beryllium fluoride and carbon dioxide. So to start with beryllium fluoride. Beryllium has a total of 2 valence electrons and each of the fluorine has 7. So 2 7s are 14 plus 2 is 16 electrons to play with. The central atom will be beryllium and we put the fluorines around the outside. Start with a single bond. Complete the octets for the outer atoms. Check the electron count, 2, 4, 6, 8, 10, 12, 14, 16, which is 16 electrons. Now beryllium is special, it's non-octet and wants a total of 4 electrons around it, and you can see it's got 2, 4, so its electron dot diagram is finished. You can see here that we need to spread these bonds as far apart as possible. And to do that, to spread 2 bonds as far apart as possible, you can see that you would have a bond angle of 180 degrees, which means this is a linear molecule. Now let's try carbon dioxide. Carbon dioxide, carbon has a total of 4 valence electrons and each of the oxygens has 6. So this is 2 6s are 12 and 4 is 16 electrons. Start with the central atom is carbon, put the oxygens around the outside and start with a single bond. So complete the octets for the outer atoms, 2, 4, 6, 8, 2, 4, 6, 8. Check your electron count, 2, 4, 6, 8, 10, 12, 14, 16, yes, but our central atom doesn't have 8, so it is incorrect. Now start by putting in a multiple bond, 2, 4, 6, 8, 2, 4, 6, 8. Check your electron count, 2, 4, 6, 8, 10, 12, 14, 16. Use the right number of electrons, but our central atom only has 2, 4, 6, which is incorrect. So now put a second double in. And this time you can see our central atom has 2, 4, 6, 8. Now in terms of molecular geometry, a double bond counts as 1 bonding pair. So in this particular case we have 1, 2 bonding pairs around the central atom, the same as the previous example, 1, 2 bonding pairs around the central atom. To spread those bonding pairs as far apart as possible, you would have a bond angle of 180 degrees, which means you have a linear shape. So for 3 atoms with 2 bonding pairs, you end up with a linear shape. What I've constructed here is a picture of carbon dioxide. Remember, the double counts as 1 for molecular geometry, but if you take the central atom to the central atom, you can see, linking the nuclei together, that you just get one long line. Its bond angle is 180 degrees, which makes it a linear shape. Now let's try BCl3. BCl3, boron has 3 electrons and each of the chlorines has 7. So 7 3s are 21, 24 electrons. Boron is in the center, chlorine, chlorine, chlorine. Remember, boron is non-octet, which means it only wants 6 electrons around it. Now in this particular case, you'll see here that boron only has 3 bonding pairs around it. And to arrange 3 bonding pairs and the most spread out as possible will give you a shape of triangular or trigonal planar. So it'll spread them like this. Now sulfur trioxide is something similar. Sulfur has got 6 plus 3 6s, 18, which is 24 electrons. So if you start with singles for your electron dot, complete the octets. So you've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Sulfur doesn't have 8, so that's incorrect. Try again, double bond. Complete the octets. And this time you'll find that sulfur has got 2, 4, 6, 8 electrons around it. You'll notice here that this double bond counts as 1 bonding pair, so it has 3 bonding pairs. So it arranges itself in a trigonal planar arrangement, which you can see in this particular case. Draw the lines. It's a triangular or trigonal planar. Bond angle is 120 degrees. This time we're going to try 4 atoms. We're going to do CH4. The carbon has got 4 valence electrons plus 4 times 1 is 4, so we're dealing with a total of 8 electrons. The central atom will be carbon, and put the single bonds of hydrogen around it. Now, in this particular case, you can see to spread these as far apart as possible. On paper, it looks like a square shape, but remember, we're talking about 3-dimensional space. So to spread them as far apart as possible, you can see here the 4 bonding pairs have been spread in a 3-dimensional element, and that 3-dimensional gives a bond angle of 109.5 degrees. And this particular shape is called tetrahedral. And tetrahedral occurs when you have 4 bonding pairs around the central atom. This time, once again, we've got 4 atoms. We're going to look at ammonia. Now, with ammonia, you can see that the nitrogen has got 5 valence electrons, plus each of the hydrogens has 1. So we're playing with 8 electrons. Nitrogen is the central atom. And completing the electron dot diagram here, you can see that we have 3 bonding pairs and 1 non-bonding pair or lone pair. So, this wants to arrange the bonding and non-bonding pairs apart as far as possible. So you can see here that it's arranged these non-bonding and bonding pairs in a tetrahedral fashion. However, we actually don't describe what we can't see, and we can't see a lone pair of electrons. So we actually describe the geometry of where the atoms are, and you can see here that the geometry is pyramidal. So the bond angle in this case is 107 degrees. You'll notice it's slightly less than for tetrahedral, and that's because the lone pair of electrons exerts a stronger repulsion than the bonding pairs. This time we're going to look at 3 atoms. I'm going to look at water as an example. So you've got 2 times 1 for hydrogen plus oxygen is 6 is 8 electrons. We'll draw the electron dot diagram, which looks like this. You can see here that we've got 2 bonding pairs and 2 lone pairs of electrons. This wants to arrange those pairs of electrons as far apart as possible to prevent repulsion. Now, to do that, it will arrange them in a tetrahedral fashion. However, when describing the molecular geometry, we don't describe where the lone pairs are. We describe the angles between the atoms. And this particular case, the angle is 104.5 degrees. It is less than the tetrahedral because those 2 lone pairs exert a stronger repulsive force and squash them closer together. You can see that this particular shape is V-shaped, and you can definitely see the V, or we call it bent. Our last example is sulfur dioxide. So sulfur dioxide has got 6 electrons for sulfur plus 2 times 6 is 12. So it is 18 electrons in total. Central atom is sulfur. Complete the octets for the outers. Check your electron count. 2, 4, 6, 8, 10, 12, 14, 16. Spares on the central. Does the central have 8? No, it doesn't, so it's incorrect. Try again with a double. Check your electron count. 2, 4, 6, 8, 10, 12, 14, 16, but the spares on the central. So you can see here that sulfur dioxide has got 2 bonding pairs. Remember, this double bond counts as 1, and 1 lone pair of electrons. So it's going to try and arrange these as far apart as possible. And we've seen previously to arrange 3 sets of electrons as far apart as possible, you would arrange it in a triangular planar or trigonal planar arrangement. And you can see here, there's your trigonal planar arrangement. However, when describing molecular geometry, we don't describe the lone pair of electrons. We only describe where the atoms are. So it's tried to arrange the electron pairs in a trigonal planar fashion, but as we only describe where the atoms are, this would once again be called V-shaped or bent. However, the bond angle is slightly different. This one's about 119 degrees because the lone pair of electron exerts a stronger repulsive force, squashing them slightly closer together. Now it's time to try some yourself. Go to the OneNote, under intermolecular forces, try shape and polarity, and try a few examples.